Hello everyone. This session is related to feedback circuits. Let's wait for 5 minutes, then start. Okay, so we'll just start. As I said, this topic is about, this week was about feedback amplifiers. So feedback is, you have input here, this is your transistor, this is your output here. Feedback is feeding back some portion of output at the input, right? This is your feedback. So we will see what are the different types of feedback. Then we will see, and we will also talk about different types of amplifiers. There are four types of amplifiers: voltage amplifier, current amplifier, transformator amplifier, and transistors amplifier. And then we will see feedback amplifier topologies and what are the characteristics of negative feedback amplifiers. And we will see a little bit about their analysis and performance comparison. We won't study the oscillators here, we will just go through feedback. Okay, so as I said, feedback is the portion of output signal is taken from the output of the amplifier and is combined with the input signal. So as I said, if this is the transistor, you will take some portion of your output and feed it at the input. This is the concept of feedback. And why we need the feedback? Because we want in our circuit distortion as low as possible. We will see how it helps in distortion. And also, the gain must be independent of external factors. External factors include environmental change, temperature, stress, strain, these kind of things. So these are external factors. This picture will give a clear representation of feedback amplifiers. Here it's shown, this is a basic amplifier with a gain A. That means it will be, let's say, a simple transistor. And it has a gain that is GM. And now, in feedback, you need four components. One, two, three. Number one is mixer. Okay. Number two is your main transistor, main amplifier. Number three is your sampler and your feedback network. A here represents gain of the amplifier without feedback, right? That is completely understood. That will be x naught by xi, that is the signal here divided by signal here. AF gain of the amplifier with feedback, that means you have this feedback as well. Then if you check the gain, that will be final, that is x naught. Or here also, you can check here the gain as well, it's because voltage will be same here across these terminals. So this is x naught by xs, it will be the same. Beta is your feedback ratio, that is phi f by phi naught, and x is the voltage or current, right? Here, talking about these ones. So these phi naught, phi f, phi naught, phi f, these can be currents or voltage. Now we will have two types of feedbacks, right? Positive feedback and negative feedback. If the signal, if the feedback signal is in phase with the input signal, what does that mean? It means that if the input signal increases, the feedback has the same phase, that it is, like say, let's say it has a lesser amplitude, but it follows the same cycle, it has the same cycle, same wave. Same case means if this is my input signal and the feedback signal also follows the same waveform, then it is in phase, right? So if the signal is in phase with the input signal, then the net effect of feedback will increase the input signal, right? You have to add this, so it will get amplified in, right? That's what it said here, the increase in the input signal. This type of feedback is said to be positive or regenerative feedback, right? This is again the representation here. The x naught a x1 is taken as a feedback. X naught is beta times x naught is taken as a feedback. Fed to this. This is a mixer. What does mixer do? It gives us the difference of the two signals. Here it is xs, then here it will be xs plus minus xl, right? So this is our input, rightly written here. Okay. Also, as I said, it has a gain of A, then what is the gain of the whole system? When you do the calculation, you'll find that it will be 1 plus A times B. Here it's represented 1 by A minus B, but here beta will be taken as a positive. Here the beta is negative. So this is the gain of the circuit with feedback. Now what is AB? The product of open loop gain. Open loop gain is A, and the feedback factor, that is B beta, is called as a loop gain. So loop gain is A times beta. If AB is magnitude of AB is 1, then AF is infinite. Hence the gain of the amplifier with positive feedback is infinite, and the amplifier gets output signal without any. So this is an important thing in case of oscillators. Oscillators is when you apply the signal, then they work on their own, right? So this is the concept of a positive feedback that is used in the oscillators. Now, what is the disadvantage of positive feedback? You know that if there are oscillations in a circuit, this leads to instability, right? So it increases the instability, reduces the bandwidth. Bandwidth is the region of operation. So if this is the bandwidth, then this will increase the distortion and noise. We will see. Now, next thing is negative feedback. If the feedback signal is 1 second. I forgot to turn on the camera. So now we'll see what is the negative feedback. If the feedback signal is out of the phase with the input signal, then the net effect of the feedback will decrease the input signal given to the amplifier. And correspondingly, the output signal is decreased. This type of feedback is said to be negative or degenerative feedback. It is, well, if this is the input signal, then you apply a feedback that is opposed in the opposite phase. So your total input signal will decrease, right? In this case, your gain will be A divided by 1 plus AB, right? So advantage negative feedback is increasing the bandwidth. It helps to modify the input and output impedances. We will calculate these things in the numericals. And you have the decrease in the distortion and noise. Disadvantage of the negative feedback is it reduces the voltage gain. We'll see about it. Now, as I said, there are now before we go to the configuration of feedback amplifiers, let's see what are the different types of amplifiers because it's important and it will be important for us to understand them properly, then we can do the numericals. Okay, so we will see also about input and output impedances of amplifiers. And now the amplifiers can be classed into four broad categories. That is voltage, current, transconductance, and transistance amplifiers. Right? So what is a voltage amplifier? See the circuit. You have input that is voltage and output that is in the form of amplified form of input that is also in the voltage. Let's see what is the definition of the voltage. If the amplifier input resistance Ri is large compared with the source resistance Rs, so what will it do? Ri is very large than Rs. And what will happen is whole Vs will drop across the Ri. That is the intention, right? That is the intention. The whole voltage is delivered here, right? So this will give maximize your voltage gain because your input is increasing. So then Vi is Vs. And at the output side, if the external load resistance RL is large compared with the output resistance R0 of the amplifier, then V0 is equal to AV, Vi is equal to AV Vs. Similarly, at the output, R0 is less in comparison to RL, whole output potential will drop across the RL, and your V0 will be simply equal to A times Vi, which we have already said that Vi will be nearly equivalent to Vs. So this is the important thing that is has to be kept in mind for voltage amplifiers is that your input resistance should be as high as possible and your output impedance should be as low as possible. These amplifiers provide a voltage output proportional to voltage input, and the proportionality factor does not depend on the magnitude of the source of the resistance, right? That is the AV. It doesn't depend on these impedances. Hence, this amplifier is called as a voltage amplifier. And the ideal voltage amplifier must have input resistance that is to be infinite, right? And your output resistance should be zero in case of ideal amplifiers. And in case of practical world, Ri should be very, very large than Rs, and RL should be very, very large than RL. Next is current amplifier. So current amplifier, the configuration is in this way. We know current passes through the lowest resistance path. So if I want to deliver the more current with my transistor, so what should I do? Your Ri should be very, very less than Rs. That is quite the opposite of the voltage amplifier, because Ri in case of voltage amplifier should be very, very large than Rs. But in case of current amplifier, Ri should be very, very less than Rs, as the whole current flows through this resistor. Similarly, at the output, R naught should be very, very large than RL, right? Now, if RL is R naught is, let's say, infinite, and Ri is zero, whole current flow will flow through this branch, and whole current will flow through this branch. That is the ideal case, and that's what the current amplifier is. And your whole current, amplified current, will flow through the load. Okay, so this amplifier is called as a current amplifier. And ideal current amplifier must have zero input resistance and infinite output resistance, as I said. For practical cases, Ri should be very, very less than Rs, and R naught should be very, very large than RL. Next is transconductance amplifier. Transconductance, we have come across this term what many times. Transconductance will be, this is Gn, right? That is I by dV, right? So here output will be current and your input will be voltage. That is the transconductance amplifier. So in case of transconductance amplifier, let's see the circuit. So what should be Ri? Right? Ri should be very, very greater than Rs. And similarly, what should be R naught and RL? Since whole current has to flow through this load, so R naught should be very, very higher than RL. This is the condition for transconductance amplifier. Now we have the transresistance amplifier. That means output will be voltage and input will be current. That will give me transresistance amplifier. Right? So what will be the condition for these resistors? Right? So, right? So it will be Ri should be very, very less than Rs, and your RL should be very, very greater than R naught, right? So such that whole voltage will drop across RL and whole current will flow through Ri. Okay, now we understood these basic amplifiers. Now next thing is how we apply them in the feedback network. So as we said, there are three types of network, three types of things that are important in these feedback circuits. That is a sampling network, feedback network, and mixer network. And we have the amplifier. That can be a current amplifier, voltage amplifier, transistors, and transconductance amplifier. In each of these circuits, the amplifiers we studied, we can sample the output voltage or current by means of suitable sampling network. So sampling network is important. Sampling network will give us either voltage or current. And apply this signal to the input through a feedback two-port network as shown in figure 1.2. So we sample either current or voltage, then we give it to feedback network, then we have here either IF or VF. Then it is applied to the comparator that either mixes IF or voltage here, right? Now let's see what is a sampling network. There are two ways, as said already, to sample the output according to the sampling parameter, either voltage or current. The output voltage is sampled by connecting the feedback network in shunt across the output, like this. If we connect, this is called as a shunt network. If we connect our circuit feedback network in this way, so it will sample voltage, right? This type of connection is referred to as voltage or no-volt sampling. The output current is sampled by connecting the feedback network in series. Now, if we connect it in series, like this way, so this current will flow through here as well. So now beta times I naught will give me here something, either voltage or current, right? So this is a current sampling or loop sampling. So you connect it, your circuit in a loop, that is series. Now we have feedback network. It may consist of resistors, capacitors, inductors, because beta will be always less than 1. So this is not a two element circuit. It's feedback network. Just simply pass a network circuit so that the gain is less than 1. It provides a reduced portion of output as a feedback signal to the input of the mixer network. It's given as this one. Or beta is the feedback factor or feedback ratio. The symbol beta used in the feedback circuits represent feedback factor, which always lies, as I said, between 0 and 1. Okay, so don't confuse it with the beta, that is the current gain in the amplifiers. This is different. Now we move on to mixer networks. Like sampling, there are like sampling we have voltage and current sampling. There is a mixing uh, tool that is of two types. One is voltage mixing. Next is current mixing. By using the series input connection, you do the voltage mixing, and shunt input connection will give you the current mixing. Like here, series mixing. You connect your feedback network here. Let's say there is a potential here, something. Let's say we have this. This is a voltage simple example, and then you have IF flowing here. This is a current mixing. Sorry, voltage mixing and current mixing. Okay, what are the effects of negative feedback? It stabilizes the gain, increase of bandwidth, decrease distortion, decrease in noise, increase in input impedance, and decrease in output impedance. Important advantage of negative feedback is that the resultant gain of the amplifier can be made independent of the transistor parameters. Let's see. And we will derive this formula when doing the numericals. The negative gain of the amplifier with the negative feedback is AF is equivalent to A divided by 1 plus AB. Now, if you differentiate this term, both sides by A, you will get this formula. dF by dA is dA by dA 1 plus 1 divided by 1 plus AB. dA by dA is change in the intrinsic gain, and dAF is the change in the whole gain. Now, this 1 divided by 1 plus AB reduces this change, so this desensitizes the circuit. So sensitivity is given by 1 by 1 plus AB. Sensitivity is defined as the ratio of percentage change in the voltage gain with the feedback to the change of the without feedback. So this is how it is defined. So as we increase the feedback, as we connect the feedback, this decreases. So your circuit becomes stable. And again, we know gain into bandwidth remains constant. So if you increase the gain, you decrease the bandwidth. So bandwidth will, now if you now the gain is reduced by 1 by 1 plus AB, therefore your bandwidth will increase by 1 plus 1, 1 plus AB. Similarly, these are given as the frequency gains at mid frequency, low frequency, and high frequency. Okay. Your frequencies change as well. If your bandwidth gain increases or bandwidth, sorry, if your uh, gain reduces, then that means your upper cutoff frequency will increase and lower cutoff frequency will decrease further to increase the band. So this is the lower half, H half, lower half. So your gain reduces your frequencies as FH has gone up, FL has gone low, so your bandwidth. Distortion is again given decreased by 1 plus AB. Noise is decreased by 1 plus AB. About the input impedance and your output impedance, we will derive these in the numericals. So now we have studied about the sampling. So depending on these are two elements. These are two elements. So 2 cross 2, we have 4 combinations, right? We have 4 elements, 2 combinations. Okay. So you can sample see in you can add in series. See, the first one is mixing. This is sampling. So you can have series mixing, shunt sampling, that is voltage. You can have series mixing and series sampling, that is voltage current, simply shunt and shunt. So this is a different types of it. Let's say just give order of these. This will be voltage. This is voltage. So what is voltage network? This is again current, and this is current. So this is a current configuration. This is again a current voltage configuration, and this last one is a voltage and current configuration. So these are four. Let's just stop here, and this is I think the basics is done about it. Let's do some numericals. Let me take a 3-4 minutes rest. Stop. Okay, let's now start with the numericals. Now that we have gone through the basics, uh, can you just tell me what? Hello, can you turn off the mic? Hello. Okay. So, what is the type of amplifier we are seeing here? What is the network? This is the current sampling, right? And now, if you look at the input side, the configuration is in shunt, right? You see these two terminals from the feedback are in shunt. So this will be current mixing. So your configuration is series, that is current, and shunt, that's also current. So it's a current feedback topology, right? Now, all the values of the components are given to us. So what we have to do is we have to find I naught by Is for the ideal feedback network. And when we say ideal feedback network, we have to consider this as infinite and Rn as 0. Okay, so what we have to find is we know we have AI that is equivalent to 116, and we have beta that is 0.25. Now let's start. We can start from this node. If this is my Is is the total input current. Now it will be distributed in two, right? In and If. Initially it was only in, and your gain was I out by in. Now as your is, so sorry, in was is. Now your is is distributed in plus if, right? So your gain will no longer be I naught by I, right? So your if is given to us as beta times ix, right? Now, since Rnb is equivalent to 0, my ix will simply be equivalent to I naught. So my is will be in plus beta times ix, that is in plus beta times I naught. Now my I naught is a I in, right? Right? This is a gain, intrinsic transistor gain without feedback network. So my IS is I in plus beta times AI in. This will give me is as I in 1 plus AI beta, sorry, not b, it's beta. Now that I have is in terms of I in, now my gain is I out is AI times I in. Now my A in, sorry, if I write it here, my I in is equivalent to is divided by 1 plus AI b. My I out is equivalent to I in, that is AI is divided by 1 plus AI beta. So my gain, that is AF, the feedback, is I out by I S AI beta is given to us as 116 plus 0.25 into 116. So calculate it, you will find it as 16 divided by this equivalent to 29 plus will be 30. And this comes out to be 3.87. So this is how you calculate the gain with the feedback network. Now we're told is we have to find the value of the input resistance of the current amplified to the ideal feedback network. The values, as we said, for ideal cases 0 and infinite. Let's start. We have this as IS, this is Rin, beta X. This is infinite, so don't worry about it. This is this IF, this is Rin. Let's call it Vs. This is Vs. And my Vs is In Rin. Now we have to find, this is here, Rin. We have to find this resistance, Rin dash. That will be given by Vs by Is. So my goal is to find Vs by Is, right? So how we'll do this? Simple case here, right? Let's find a case here. My Is will be In plus If. And can I write it directly as In plus beta times I naught? I can, right? And we know it is equivalent to AI beta times In. So my Is is In 1 plus Pi times beta. So my IVS is In times Rin. So I have to just substitute it. We'll get Vs is equal to Is Rin divided by 1 plus times beta. So my Vs by Is, that is my Rin dash. will be equivalent to Rn divided by 1 plus S beta. So my Rn dash is, let's calculate it. My Rn is given to us, Rn is 3 kilo ohm. Right? So what did the feedback do? What did the feedback do is reduce the input impedance, right? It reduced the input impedance. That was the important thing, right? Okay, so this was about. The next one is find the output resistance. Okay, so just see this. Okay, since we are connected to the feedback, so we have to consider the input circuit as well. Otherwise, in calculating of the output resistance, we don't consider it. But here we have to. This is another equal to 0. Mm, okay, so this is my so to calculate the output resistance, let's calculate it from here, and this will be opened here. So my I out is simply equivalent to, let's call it V out, V out here. That is V output by R out plus I in, right? My I in, if I apply a voltage analysis here, I'm sorry, current KCL here, this will be I in plus IF is equal to 0. I in will be minus IF, that is minus beta times Ix minus beta times Ix, that is minus beta times I naught. Okay, so my I naught is equivalent to V naught by R out minus AI times beta times I naught. This will be I naught plus AI beta dash. I naught is equivalent to V out by R out. If I take I naught as common, so my V out put by I out, that is my R out dash is equivalent to R out 1 plus AI times beta. Right? So output impedance increases. Now let's calculate the value. R out dash R out is 4K. This comes out to be 120 kilo. So this is how we do the output resistance. Now the next thing we have to do is we have to calculate these input and output resistance again, but this time we have to consider R in B as 150 ohm and R out B as 6 kilo ohm. Okay. So this will, if the feedback network is not ideal, this will change my beta. First it was 0.25 Ix. Now this will change. Also, gain will also change because now you have around the 6K, RM is 151, this is 6K. IS. Initially, the IF current flowed through only this network. Now we have another resistor that is 6K. So my IS will flow through I in 6K and R in 6K, and this is beta IX. So now what we can do is we find the Rn, right? Then take it as parallel to R out, right? Or what we can do is we should just let's just calculate it. So my IS will be IF plus I in, right? Now my IF is VS by R out do plus beta times IX, right? My IS will be Vs by R out D plus beta times Ix plus I in. My Ix this time is not directly equivalent to I naught. There will be a current distribution or loading output. So my Ix will be equivalent to R in, sorry, this is not. Current doesn't distribute in this way. That will be R out divided by R in beta plus R out. That is 3, 4, 3, I guess. I guess it's is 150 ohm plus 4K. Let me just see what it is. Point 0.96. Okay, so my beta is equivalent to 0.96. I know. Let me just calculate it. That comes out to be 0.24. Oh, so beta dash will be equal to 0.24. One thing is goes due to the output loading. Now, what about the input? It will change as well, right? So let's for time being take it as this value and do the further calculation. So we reached here, right? So, this means my IS will be equivalent to Vs by R out D plus beta dash times directly writing it then plus my Vs is sorry my Is is R out D plus I in 1 plus times beta dash. Also my Vs is I in R in my Is will be I in R in R out beta plus I in 1 plus. right? So my in will be effectively equivalent to R out P divided by Rn plus R out P 1 plus Is. Vs as said earlier is in Rn. Vs will be equivalent to out into Rn into Is divided by Rn R out P. Rn dash is Vs by Is equivalent to Rn is 3k into 6k divided by 3k plus 6k into 1 plus comes out to be 99. So this is about the input. Now similarly, we can do the output as well, right? So if we will solve this question, you will see that uh, using these elements as well. One thing is you can directly put it in series of the previously related. So my R out mu is simply equivalent to Rn B plus R out 1 plus A iota B. One thing we have to do is, in case of non-ideal, what is the AI and beta? These values also change. Please calculate it. Calculate these values. Okay. Let me just give the answer. Mm, Answer is 81.5 ohm. That is 0.0. Okay. I'm not feeling well, so I guess I will stop here. We will continue hopefully in the next session. And we will also do there are a few more questions related to this topic. We will do that as well. Yes. If there are any questions, please post in the comment boxes. If you want the PDF as well, I will share that too on the press. Let's just end the session here.